Hi, I'm going to be teaching you lesson 8.3 on page 132 through 134. I'm not really referencing to the book, but to just keep on track of what page that's on. Also, there's an activity page where you can get more practice on page 136. That's also helpful. But today we're going to get started with some introductory of this topic. So I'm doing 8.3, but this is 8.1, where we introduce imaginary numbers. Well, the definition, straight out of your book of imaginary numbers, is any number of the form of bi, where b is a real number and I is equal to the square root of -1. Okay, so in terms of words, we can kind of process that a little bit. But just to put it in numbers, here's an example. So we're going to start off with this equation, just solving for x. So you look here, the first thing you see you have to do is subtract 25 from both sides. Okay, that's simple. Then you see, okay, it's x squared, so I have to square root x squared, but I also have to do it the other side. Okay. But then you see here, oh no, you can't square root negative numbers. Well, you can now, because imaginary numbers, we can. That allows us to do that. So the way you do that is that since I is equal to the square root of -1, we can say that square root of -1 times the square root of -25, a negative times a negative equals positive, would be I square root of 25. Okay. And we know the square root of 25 is 5, so that would give us x equals 5i. In terms of imaginary numbers, it can sometimes confuse people. Like, why do we use this? Why can't we just say, oh, no solution, we can't square root a negative number? Well, long ago that was the case, but they now came up with the way that we can complete the problem and use this just like we used integers, or like we use a number divided by 0, which is undefined. It's the same thing. Okay, to further introduce kind of this topic, in 8.2 we talked about complex numbers and complex conjugates, but I just want to re-explain it to you because it's going to be something that's coming up here in 8.3. So a complex number can be defined as it's a number in the form of a plus bi, where a and b are real numbers and I is equal to square root of -1. Okay, well, we already know this. We just talked about this of when we were talking about imaginary numbers. But what this is saying is that when we see an expression in the form of a plus bi, where a and b are real numbers and I is the imaginary number, it's a complex number. Okay, so now moving on to complex conjugates. It's kind of hard to define, but what this is telling you, it's saying that it can be defined when saying that the complex conjugate of a plus bi, which is your complex number, is a minus bi. So basically you have your complex number, but the complex conjugate of that just has the opposite sign. You can kind of see that there. Just for some further knowledge of this, here's a couple examples. So if I have, see, this is in the form of a plus bi, so this is our complex number, so 5 plus 9i, so our complex conjugate would be 5 minus 9i. Just another example. if you have negative 2 plus 2i, which is our complex number, our complex conjugate would be negative 2 minus 2i. So I just want to make sure that we're just changing our signs here. Okay, so now that we got that out of the way, we can actually focus more on what's in lesson 8.3. So from talking about what imaginary numbers are, what complex numbers are, what complex conjugates are, we can now take this one step further and say that lesson 8.3 is factoring with complex numbers. So, taking that into consideration, just this in general is this little expression can be factored out as a plus bi times a minus bi. Well, from talking about what complex conjugates are, a plus bi has a complex conjugate of a minus bi. So these two are complex conjugates. With that being said, you can actually use complex conjugates to factor quadratic expressions that are in the form of a squared plus b squared. Okay? And this is kind of just showing you how that's possible. So a times a is a squared. A times negative bi is negative abi, and then bi times a is just positive abi. So looking at that cancels out. So then you're left with positive bi times negative bi. So you get negative b squared times I squared. So actually it would be a squared minus b squared times I squared, and that I squared is actually negative 1. So a negative times a negative is a positive. That's why we get a squared plus b squared. So that's just kind of how you check your answer. Okay, so now I kind of want to talk about like what the relationship is, and we just kind of explain that as complex conjugates. You can just see like the two signs are different, so you know it's complex conjugates. Okay, moving on to examples of how to factor this out. So if I gave you an example of, let's say, 25x squared plus 36 equals 0. Okay, so this equation, looking ahead, you can see that these two can be square rooted, and you can see like 5 times 5 equals 25, 6 times 6 equals 36. Okay, so the way you do this, the way I like to do this when I write it out, is have 5x squared, so 5 times 5 equals 25, okay, and plus 6 squared, okay, 6 times 6, 36, okay, equals 0, gets a 0, and then you can see that it's actually in the form of a squared plus b squared equals 0. So yeah, but now we want to take it more and put it into like factoring would look like. So since we know that we know from up here that a plus bi times a minus bi. They're both complex conjugates, which means that we can put this into the form of that. So we can say 5x plus 6i times 5x minus 6i and set it equal to 0. So now that we have this, we can solve it just by like normal factoring that we would. So 5x plus 6i equals 0, and 5x minus 6i equals 0. So then you just solve it normally. You subtract 6 from both sides and then divide by 5. So x equals negative 6i over 5. And then x over here equals 6i over 5. So that's how you solve for x using complex conjugates. Just another example I can give you. This one, it's simple, but it's going to be a little harder. Just something more to think about. Okay, so example number 2 is going to be 16x squared equals negative 49. Okay, well, it's not in the form of a squared plus b squared yet, so we can move the negative 49 over to make it positive 49. So 16x squared plus 49 equals 0. So now that we got it set to 0, we kind of just want to do the same thing that we did in the last example. Excuse me. So just write it out is what I like to do. So the square root of 16 is 4. So 4x squared. So 4, 16, okay. And then 7 squared, 7 times 7, 49, equals 0. So this is in the form of a squared plus b squared. Okay, I'm good. And now we want to put it into the a plus bi times a minus bi. So it's factorable. Okay. So now we just kind of do what we did here. So 4x plus 7i times 4x minus 7i equals 0. Okay, so now that we have it in the form of the complex conjugates, we just simply solve like we would in normal factoring. So we set both little expressions to 0, which makes an equation, but just to see here that you should first subtract or add 7i to both sides and then divide by 4. So you get x equals negative 7i over 4 and x equals positive 7i over 4. Or another way you could write it, when you realize that you're using complex conjugates, is when you can just do x equals plus or minus 7a over 4. Okay, just so I don't take up too much more of your time, I'm just going to do one more example. It's a little harder than the past 2 examples. So, if I give you 9x squared equals negative 20, well, first we can say that we want it in the form of a squared plus b squared, so we can move the 20 over. So it'd be 9x squared plus 20 equals 0. So, okay. So when you look at this, you can say, okay, 9 can be square rooted into a real number, which is 3, but 20 doesn't exactly do that. But that's okay, because we can still use complex conjugates for factoring and solving for x. So, let's just go ahead and write out 3x squared plus, okay, so what goes here? So, when you look at this 20, what we're doing here is that we're just square rooting it. So if we want to square root 20, it gives us square root of 20. But if we multiply it again by square root of 20, or like we're doing 3 times 3 equals 9, square root of 20 times square root of 20, equals 20. So here we can put the square root of 20. And this is now in the form of a squared plus b squared equals 0. Okay, so pretty much we do what we did in the last 2 examples. We put it into the complex conjugates form. So 3x plus square root of 20 times 3x minus square root 20 equals 0. Well, we don't exactly want to jump to the next step yet for solving for x, because 20 can still be written differently than just square root of 20. So, taking that into consideration, square root of 20 can also be written as square root of 4 times square root of 5. So you can square root that, so it's 2 square root of 5. So this would be written as 3x plus 2i square root of 5 times 3x minus 2i square root of 5 equals 0. I didn't put the square root of I right here. Like I said, people forget to do that. Please don't forget to do that. It's really important there. Anyway, now we can just solve for 0. So 3x plus 2i square root of 5 equals 0, and 3x minus square root equals 0. Okay. So if we solve, x would equal negative 2i square root of 5 over 3, and x over here would equal 2i square root of 5 over 3. Again, you can also write that as x equals plus or minus 2i square root of 5 over 3.